This table details the properties of two specific coordination complexes. On the top row, we have an iron ion bonded to 6 water molecules. Just below it, we have an iron ion bonded to 6 cyanide molecules. Both of these structures are built around the exact same core, a central iron ion, yet they behave entirely differently. The water-based complex is highly magnetic and distinctly colored. The cyanide-based complex is diamagnetic, meaning it produces no magnetic field, and it is visibly pale. Standard covalent bonding models, which assume electrons are shared evenly between atoms, do not account for this divergence in physical properties. If the bonds were identical in nature, the physical results should be identical. To understand why these compounds behave this way on a macro level, we have to look past simple electron sharing and examine the microscopic, three-dimensional geometry of their electrostatic environment. The scientific framework used to solve this specific paradox is called crystal field theory. Crystal field theory operates on a strict geometric assumption. Instead of treating the surrounding molecules, the ligands, as complex covalent partners, we strip them down to simple negative point charges. The central metal ion has its own electrons, which are also negatively charged. When this rigid cage of negative point charges presses inward, the metal's own electrons are naturally repelled by the incoming field. By mapping exactly where these negative charges sit in three-dimensional space, we can calculate the resulting electrostatic clashes and predict the molecule's behavior. Chemical properties like magnetism are direct mathematical consequences of spatial geometry and electrostatic repulsion. We start with a free transition metal ion in a vacuum. Its valence shell contains 5 d-orbitals. In this isolated state, these orbitals are degenerate, meaning they all sit at the exact same energy level. If a perfectly spherical cloud of negative charge surrounded this metal, all 5 orbitals would experience equal repulsion and their overall energy level would rise uniformly. But real coordination complexes are not perfect spheres. In an octahedral geometry, 6 ligands approach the central metal from strictly 6 distinct points, tracking exactly along the x, y, and z Cartesian axes. 2 of the d orbitals, the EG set, have lobes that lie directly on these axes. As the ligands approach, these orbitals suffer a massive direct electrostatic collision, pushing their energy levels significantly higher. The other 3 orbitals, the T2G set, have lobes that point diagonally between the axes. This allows them to effectively dodge the direct incoming charges, experiencing less repulsion and settling at a lower relative energy. This uneven three-dimensional layout breaks the degeneracy. The collision geometry physically splits the once equal d orbitals into 2 distinct energy tiers. This diagram illustrates the splitting of d orbitals in an octahedral complex. It maps the transition from a hypothetical spherical field on the left to the split T2G and EG tiers on the right. The physical gap created between these 2 new energy tiers is the crystal field splitting energy, denoted by the symbol delta naught. Total energy is conserved relative to the spherical average. This center line acts as the barycenter. The 2 upper orbitals shift up by positive 0.6 delta naught, while the 3 lower orbitals shift down by negative 0.4 delta naught. This equation is used to calculate the crystal field stabilization energy for the entire molecule. It totals up how many electrons fall into each tier to determine the net energy change. We can now predict exactly how much stability a molecule gains simply by letting its electrons drop into those deeper, less repulsive T2G orbitals. This model encounters a structural problem when a molecule has 4 valence electrons. The first 3 fill the empty slots in the bottom tier, but the 4th electron has to make a choice. It can squeeze into an already occupied orbital in the bottom tier, but doing so incurs pairing energy, an intrinsic thermodynamic penalty caused by forcing 2 negatively charged electrons into the exact same localized space. The alternative is jumping to the upper tier. The size of that jump depends on the ligands. Different ligands create different splitting energy gaps, as ranked here in the spectrochemical series. If the ligands produce a weak field, the gap is small. The pairing energy penalty is too high, so the electron takes the path of least resistance and jumps to the higher empty tier. We call this a high-spin configuration. If the ligands produce a strong field, the split is massive. The gap is too wide to jump. The electron is forced to pay the pairing energy toll and crowd into the lower tier, creating a low-spin configuration. A molecule's internal architecture is governed by a strict thermodynamic competition between the pull of geometry expanding the gap
and the push of localized electron repulsion forcing them apart. This brings us back to the iron complexes we examined at the start, identical metal centers yielding completely different magnetic behaviors. A molecule's spin state determines its unpaired electrons. In this magnetic moment equation, N, the unpaired electrons, is the exact source of the magnetic field. High spin complexes maximize unpaired electrons, creating a paramagnetic reading. Low spin complexes force pairing, zeroing the magnetic field. The abstract geometry of orbitals predicts the physical, measurable reality of magnetic attraction in the laboratory. We can test this model further by changing the geometry entirely. Instead of 6 ligands in an octahedron, consider a molecule with only 4 ligands arranged in a tetrahedral shape. This diagram illustrates a tetrahedral complex. Ligands approach from different angles, missing the Cartesian axes and colliding with off-axis orbitals. Because this geometric approach is inverted, the energy splitting flips upside down. The T2 tier is now pushed higher than the E tier. Because fewer ligands are involved and they do not hit the orbitals head-on, this tetrahedral split is much smaller. The system almost exclusively favors high-spin configurations, proving the model scales to new geometries automatically. Across all of coordination chemistry, complex macroscopic behaviors, from bright colors to intense magnetism, are born strictly from inescapable rules of three-dimensional geometry and electrostatic limits.